So we discussed about the semiconductor. Let's say this is a semiconductor. So this is a material which has the conductivity higher than that of the insulator, but much less than that of the conductors. But what we can do, that if we could add some impurity to it, then we can really enhance its conductivity, right? And then we call it semiconductor, because its conductivity is between conductors and insulators. So when you mix it with the impurities, then you call them to be extrinsic semiconductor. In the pure state, they are not very useful, and you call them the intrinsic semiconductor. The examples are germanium, silicon, gallium arsenide, which is a composite. These are the examples. Germanium people are not using. This is the most popular one. Extrinsic is you can make different kind of impurities, two kind of impurities, trivalent and pentavalent.
Pentavalent.
These are also called as the acceptor, and these are the donor. So these are called as the p-type semiconductor when you mix them with this impurity, and here you call them n-type.
N-type, yes.
So the charge carriers, majority charge carriers here are the holes, and in this case are the electrons.
Electrons, yes.
So what people did, they chose two different kind of semiconductor material and put them side by side. Made a junction out of it. This become a PN junction diode. And what happens? That a region is created, which region is known as the depletion region, and that also creates a potential barrier between these two electrodes. So this is known as the diode. Different kind of diode, different kind of applications are there, but we discuss the major properties. We discuss their VI characteristics. So this is the unbiased diode, but we can bias it. So we can either put it in the forward bias. So for that, the characteristic will be this. Or we can put them in the reverse bias, connecting P with the negative and N with the positive. In that case, the characteristic will be this. So this is breakdown voltage, this is V voltage, this is reverse saturation current, and so on. So these are the properties we discussed. And diode, the most useful application of the diode is the rectification, rectifier. Full wave, half wave, bridge, and so on. Those things I think you remember from your MSCs. The most important thing which you can do with the semiconductor is to make the transistors. So why only two? Can we keep three diodes side by side? So N, P, not three diodes, three pieces of semiconductor side by side. So in that case, this becomes the emitter, this becomes the base, this becomes the collector. And the emitter diode is basically the forward bias, and this one is the reverse bias. And this, I made a mistake. So generally the emitter is made common. So this is not the correct picture. So that's why we call it common emitter configuration. You can get three different kind of configuration: common emitter, common base, and common collector.
Common collector.
Yeah. So the schematic is this.
Yes, yes.
This will be the direction of current for NPN transistor. So this is your base, this is your emitter, this is your collector. You make this as a forward bias. This is the emitter. Now you will make it common. This will be grounded. And then you can this is how you make the transistor. Plus, minus, plus, minus. This is RC, collector resistance. We can have resistance here also. RB. This is the voltage VBB. And this is VCC. So this is your common emitter configuration. Right? And we discuss how to analyze this. There were 3 steps. First step was that first you need to find out the base current. So the base current will be the current flowing through the base. Will be basically VBB, this supply, minus VBE divided by RB. That will be the base current. Because direction of current is like this. It is coming from collector and it is getting this. The base current will be flowing in this direction. This is the direction of collector current. So the base current will be, so this is the voltage VBB, then some voltage will be dropped across this RB. So this is the point where you want to know the voltage. So this is VB, base voltage. Here it is VC. And of course, this is VE. And in this case, V is 0 because this is grounded. Right? And what will be the voltage between VB and VE? That will always be that of equal to the potential barrier. So VBB minus VCE, VBE, which is 0.7 divided by RB. So this is the first thing you do. And if VBB is roughly typically 20 times larger than this, if it is let's say 14 or 15 volt, then you can ignore this 0.7. But if it is let's say 5 volt, then it is a good idea not to ignore that 0.7. Because ideal diode case, in case of ideal diode, there should be no potential barrier. The thickness of the depletion layer should be 0. This is first case, IB, VBB, and this. So we can check what will be the base curve, base characteristic, IV characteristic for base, which is simple because this is forward bias. If you increase the VBE, you will get this kind of behavior, forward characteristic of a diode. Because the emitter diode, this one is in the forward bias, this one is in the reverse bias. Right? Second thing is now, the transistors are made to have a current gain. So current gain is IC is basically beta times IB. So that is the second step. You can find out the collector current. So beta is typically of the order of 100. So you know that IB will be smaller than IC. So IB are of the order of microampere, and this is of the order of milliampere. And the third and last step is now we have to find out the VCE between this and this, which is same as this. So VCE can be found out. This VCC will be divided by the voltage across this and voltage across this. So VCC can be written as ICRC, the voltage drop across the resistance RC, plus VCE. So this relation will give you the characteristic, VI characteristic for the collector diode. So collector diode is operating in the reverse bias. So it should show you something like this. Right? But the thing is that this behavior will be inverted. Why? That I have not done, but that can be easily verified. So what you can get, so the collector characteristic will look like this. For a given voltage VB, there will be some current IB. So for that particular, at that particular IB, because this you should have given, and there will be IC, which will vary with the DC. So this curve will be basically inverted. It will become like this. It is the same reverse curve, but with the reverse sign. This is how the I don't know whether you are seeing this. VCE and this is IC. This is how it will look like. And I discussed that this will be the active region, this will be the saturation region, this will be the threshold region. And if you change the IB, you will get different curve. Be careful. If you increase IB further, it will, and so on. So what is the meaning of this? That for voltage, let's talk about this curve. After this voltage, your collector current is not changing. इसका मतलब क्या है that all the electrons which were emitted from the emitter have been collected by the collector. उसके आगे voltage तुम कितना भी बढ़ाओ, your current is not increasing. So this part is known as the active region. Active region क्यों बोलते हैं? Because you can find the load line which comes from this relation. VCE becomes your X, the independent variable. IC becomes your dependent variable. So you get a line, equation of line, which is Y is equal to, so IC is equal to minus VCE upon RC plus VCC upon RC. Something like this. So Y is equal to MX plus C. So the slope will be negative. So you get this kind of line, which makes a negative angle from the x-axis. Right? And I told you the point where it cuts the curve is known as the Q point. Q point ka matlab there has to be some value of voltage and value of current at which your transistor is operating. And I ended with this, that this configuration is good for two kind of operation. You can either operate here or you can operate here. So this is a switching kind of situation. You can go to saturation part or you can go to here. But you never want to go to saturation part, right? Because in that case you will have lots of current and that will destroy or burn out your diode. So you can be in this saturation region. You can use diode as a switch. But for amplification, this configuration is not useful because this Q might be varying a lot. Varying a lot का मतलब क्या है? That this Q point is not fixed. You may leave this active region and you may land up in the saturation region or in the breakdown region. Right? And if that happens, or एक भी transistor अगर तुम्हारे IC में खराब हुआ, then the whole component may stop functioning. So the particularly useful configuration is, so let me tell you, how do we find out the Q point first? That I did not do yesterday. So how do you find the Q point? So for Q point, I will just give some values to these resistance and the voltage. Do that. So I have done that exercise with an example. Let me take that example only. Yes. So this is 15 volt, let's say. This resistance is 500 kilo, because that will also give you idea what are the resistance and what are the voltage and currents. This is smaller, 3 kilo ohm, smaller than the base resistance. This is 15 volt. You do not want to go beyond 15 volt, right? Because then you will get a cutoff region and so on. And this transistor has beta is equal to 100. Now, how can we find out the load line and the Q point? So the first thing, the procedure I prescribed a few moments ago, is first we have to find out the IB. IB will be VBB minus VBE. So VBB is 15, VBE is 0.7 divided by 500 kilo ohm. And now because this is more than 20 times, so I can ignore 0.7. So this is roughly 15 divided by 500. कितना आता है? 500K. So 500 into 10 to the power 3. So ऊपर जाएगा and we will get 5 3 ja. It will come out to be 30 microampere. 30 or 300? 30. So the base current is of this order, typically of this. And mind it, transistor will not operate until you provide this DC power supply. It is connected to those supply. So finding out the Q point is, finding out the load line is easy, because load line का equation क्या था? IC is equal to minus VCE divided by RC plus VCC divided by RC. So if you can find out the 2 points, then you can draw the line. And we know, because from the 2 point only a unique line can pass through. So we can choose, first we can choose IC is equal to 0. IC0 will give you VCE will be exactly equal to VCC. We are making some assumption. I'll tell you what are the assumption. So this is 1 point, that IC is 0 and VCC is equal to 15 volts. This is 1 point. And now the second way I can take VCE is equal to 0. That will give you IC is equal to, that will be the maximum possible current which can flow through the collector. So when you take VCE 0, so IC will be simply VCC by RC. And VCC is 15 volt. RC is how much? 3 kilo. So 5, 10 power minus 3. So 5 milliampere. I got the 2 points. And I can draw the load line. VCE and IC. So 1 point is 0 and 15. ये point होगा यहाँ पे. And second point will be 0 and 5. Here. So this is the maximum current, 5 milliampere. This is 15 volt. So this is the load line. And your Q point will be somewhere on this load line. Q point is also known as the operating point. How to find the Q point? So we can calculate the VCE. This is how you can vary VCE from 0 to this. All right. So we calculated IB, which came out to be 30 microampere. I can find out IC, which is beta times IB, beta being the current gain. So 100 into 30 microampere, that will come out to be 3 milliampere. IC, this is the IC. And then VCE will be VCC minus IC, the third step of the analysis. VCC is 15 minus IC, you got to be 3 in the milli, so 10 power minus 3 into RC is 3 kilo ohm, so 3 into 10 power 3. So 15 minus 9, 6 volt. So that is your Q point. 3 milliampere and 6 volt. So 6 volt ka matlab hai this is 10.5 somewhere here. This is your Q point. By the way, can you tell me how will I vary this VCE? VCE को vary कैसे करेंगे जिससे IC भी vary होगा? For that, this resistance should be variable, right? Or this variable, whatever.
Yes.
That's how we can do. Ideally, I should be controlling it here. I should make this variable, right? So IB change होगा, उससे IB change होगा, फिर IC change होगा, और फिर VCE change होगा. All right. For this fixed configuration, that's the Q point. But the problem with this base bias configuration is that it depends on beta, and beta is a very, very fluctuating parameter. So Q point यहाँ पे तुमने calculate किया, you made a transistor to operate at this point, but this point could be here or this could go here. This is not good. So what do? We use the emitter bias configuration. Emitter bias का मतलब है, this is the only thing. We remove this resistance from here, make it short circuit, no base resistor, and we add that resistance here. उसको यहाँ से हटा के वहाँ लगा and call it RE. So this is the common emitter configuration still again, but now instead of being base bias, this is the emitter bias. So emitter bias, common emitter configurations are useful for the amplification purpose. Why? Because this Q point becomes non-fluctuating. It becomes independent of beta, and hence there are chances, there are very, very almost zero chances that Q point will vary and you will not remain in the active region. If you are not in the active region, you cannot do the desired amplification and other calculations. So we want to discuss the emitter bias case, right? That's the only thing. This remains VBB. This remains RC. This is VCC. That's it. Now the analysis will change a bit. That also I have done using an example. So I'll take the example. This is now 5 volt. Instead of 15 volt, this is 5 volt. This RE is 2.2 kilo ohm. But remember, now VE will not be 0, right? Can you tell me why? This will not be 0. Because पहले ये directly grounded था. Now it will not be grounded, right? The voltage drop will be across the board.
Yes.
Right. So this will not be 0. This is 1 kilo ohm and this is 15 volt. That's it. That's what we have. So now the procedure will change a bit. First thing is we need to find out now this voltage, which is VE. This is VC. This is VB. Fine.
Yes.
Right? So what will be VE now? VE will be VBB, this full voltage, minus this VBE. So VBB minus VBE. And VBE we know will be 0.7. This is 5 volt. This is 0.7. Now we cannot ignore 0.7 because it is not 20 times. 20 times का मतलब क्या है? 5% errors, 5% से ज़्यादा error आ जाएगा if you ignore 0.7. 5% error are allowed for engineers. Physicists का पता नहीं. So VE comes out to be 4.3 volt. So this point will be at 4.3 volt.
Okay.
Okay. Now we can find out the emitter current. Second thing is we have to find out the emitter current because that is the current that will be flowing through this resistance, right? IE, which is simple to find out. The voltage drop is now across this is now VE minus this is at 0. So VE will be the voltage drop, right? And this is the resistance, so you can calculate the current. So 4.3, let me write this, VE divided by RE. So 4.3 divided by 2.2K. And this will come out to be 1.95 milliampere. And now there is no resistance, so there will be very, very little current. So as I told you that IE will be, is it made up of base current plus collector current. And base current is all very, very less, almost 0. We'll calculate that also. So IE is almost equal to IC. So this is first step. The second step, third step is you can find out IC, which is nothing but equal to IE, right? Because this plus this will make this IE. Last thing is we need to find out this voltage also, VC. अभी क्या होगा ये voltage? Collector voltage क्या होगा? We found out the base voltage which will be same as 5 volt. Emitter voltage भी पता चल गया. Base collector voltage. Fourth step. VC. So VC will be this voltage and the voltage drop across.
Drop
across,
right? 1 kilo. Yes.
So the current is flowing IC, right? So this will be VCC minus IC RC.
Yes.
Which is 15 minus IC we calculated to be 1.95 milli, so 10 power minus 3 into RC
1 kilo.
1 10 power 3. So 15 minus 1.95. And that will come out to be 13.1 volt. Roughly. $1.9, yeah, 13.05. 1.95 is not. If you add 0.5, then it will become 2. So 13. Precisely, it should be 13.05.
Cutoff voltage from collector.
Sorry?
Is this a cutoff current? Cutoff voltage?
Which one?
VC or collector voltage?
Collector voltage, yes.
I read about cutoff voltage also. So how to define them also?
Cutoff voltage क्या होता है?
और cutoff current है, sorry, voltage नहीं है, IC cutoff था. वो भी निकाला जा सकता है, मगर उसमें वो कहाँ से निकला वो थोड़ा समझ में नहीं आया था, कल मैं थोड़ा पढ़ रहा था.
Right. So cutoff का मतलब है for that current your transistor should go into the cutoff region. But what kind of cutoff you are talking about?
Before breakdown. Before the breakdown voltage maybe.
Yeah. So at the breakdown, right? So yes. So I don't know what you are talking about because breakdown voltage is higher than 15 volt. Breakdown voltage is typically of the order of 40 volt. So उससे पहले तक breakdown नहीं होगा. And as I told you, you do not want your transistor to operate in this reverse bias configuration. So can I talk to you later? I mean, after this lecture, cutoff, कौन सा cutoff के बारे में? Yes, they are cutoff voltages. Yes.
Yes, it's no problem.
But वो किस context में cutoff बोल रहे हैं उसको देखना है ना? I will discuss one in the case of operational amplifier.
Okay.
Maybe that will give you some idea what you wanted to ask. So finally, last thing, fourth and last thing is we have to find out VCE. VC is the voltage across collector and emitter. That can be simply VC minus VE. We have calculated VC and we have calculated VE. So it is 13.1 minus VE came out to be 4.3. It comes out to be 8.8 volt. So analysis has changed, right? और load line कैसे मिलेगा? Load line इसी formula से मिलेगा. VCC is equal to VC minus VE. So now your VC, how did you calculate the VC? VC is nothing but VCC minus ICRC. And then minus VE. VE is VBB minus VBE. So you see there's again the relation between VCE and IC. This will give you the load line. But the interesting thing was in this whole analysis, we did not talk about this beta. So that makes your calculations, Q points and other things. The Q point क्या होगा इस केस में? IC which came out to be 1.95 milliampere, and VCE came out to be 8.8. So this is the Q point. And this is rock solid. This is perfectly fixed. It's not going to fluctuate because this is not depending. Those calculations are not involving beta. That's why this configuration, the emitter bias configuration, is far more useful for amplification. Actually, we use this for the amplification. We do not use the base bias configuration. Does it make sense?
Yes.
Right. And then we talked about the operational amplifier. So one thing you noticed, जो output था इसमें characteristic, it was inverted. Reverse की वजह ऐसे दिख रहा था. So one thing you can say that if you apply input here and if you calculate the output here at the collector, then there will be 180-degree phase difference. So whatever input you get here, you will get reverse of that. But if you put another transistor here back to back, so now this will give you 180-degree phase, and then another will give you 180-degree phase. So finally you will get in phase. So output here and input here, they will be in phase. But input here and the output there, they still will be at 180-degree phase. So that's why one of the input terminal is known as the non-inverting. Another one is known as the inverting terminal. So that we are going to discuss very, very quickly. Operational amplifier is also known as the differential amplifier, which is a back-to-back common emitter configuration amplifier with the emitter bias, because we want to use the amplification. And we call it differential because it amplifies the difference between the two input terminals. So this is one transistor. Yeah, yesterday also I faced this dilemma. Let me see if I can do it nicely. So this is NPN. So this is the direction of current. This is emitter. This is base. This is collector. So this will be connected to some collector resistance. Let me call it RC1. This will be connected to another collector resistance. Let's say RC2. And of course, we need a VCC. So VCC for both could be the common. I hope this is visible. I will not use board above that. So this is NPN. So yes, I can apply one input here. We call it VI1. It could be a sinusoidal signal, AC signal. We can apply another signal here. And let's call it VI2. And yes, we need to connect the resistance. So So they are common emitter also, and then there will be resistance. Does it make sense? Or again I made, yeah, this is fine now.
Okay.
This is fine. And then this is a voltage. इसको बोलेंगे VEE now, right? Because we are making emitter bias. This is RE common, and output will be collected. So this is the collector voltage. We'll call it VC1, VC2. The output is taken between these two terminals. So output will क्या होगा फिर दोनों का? It will be VC1 minus VC2, right? And input is VI1 minus VI2. And this input will get amplified by some factor, that's the gain. Right? So output voltage will be, but that depends कि किसको किसके respect में ले रहे हैं. So generally we make this as a VC2 minus V1. We take this VC2 minus V1. इस तरह से लेते हैं. So this is V out. That will be equal to some gain times input. So one of the input will be, as I said, non-inverting. Another one will be inverting. So can you guess which one will be inverting, which one will be non-inverting? With the hint I just gave you. So this one will be non-inverting now, right? क्योंकि इसका आउटपुट यहाँ से जाएगा, करंट इससे पास होते हुए जाएगी. So this will give you 180 degree phase distance. This will give you another. तो यहाँ पे आते आते ये पॉजिटिव हो जाएगा. So V1 का पोलैरिटी भी आउटपुट के साथ रहेगा और V2 का. We do not want to do that analysis. It's a bit complex because we have to do really. It will take maybe one full lecture or more than that. AC and DC analysis, but this wisdom we can use. The symbol for this is so generally we do not take this. We take single terminal. We use single terminal as well. So this is grounded. Can be considered grounded. That's how we do it. So two inputs. One is inverting, another one is non-inverting. V2, this is V1. VI2, VI1, and this is V out. This is your operational amplifier. Simple. Difference क्यों बोल रहे हैं? Because you can see it is amplifying the difference of the two signals applied to two terminals. This is one, this is another. This is one, this is another terminal. This is VI1. So that is the operational amplifier. Now there are two things we should discuss about operational amplifier. First of all, what are its characteristics, the properties?
Yes.
Ideal properties. And the second thing is what are some useful applications? Those two things we are going to discuss shortly. Properties are fine. I have done those calculations. But let me look into some of the properties. The first property is that this gain for an ideal operational amplifier, this gain is
Infinity.
infinite. Yes.
Infinite.
Infinite voltage gain.
Okay.
Second property. Why the voltage gain is infinite? Can you guess?
इनपुट रेजिस्टेंस ज्यादा होता होगा.
Yes. No.
इनफाइनाइट इनपुट रेजिस्टेंस होगा तभी गेन ज्यादा आएगा.
No, you remember. अभी जो output था, V out was
हाँ
basically A times
हाँ
V
आई होता है ना?
I1 minus V I2, right?
हाँ हाँ
So A will be V out divided by V in, right?
V in.
yes yes.
And this V in is very, very small, right? Because they are
नहीं,
almost equal. If you could imagine that if they are same kind of signal, then even for finite, this will become very large. But that's a rough, yeah, I think this is just a mathematical picture, but yes, practically you are right. That depends upon the
जो
impedances,
resistance
right?
है,
Yes,
yes.
resistance will depend. You are right. So, but as I
क्योंकि
said, I do
सर
not.
गेन का मतलब ही है कि आप रेजिस्टेंस क्या सेट कर रहे हैं आउटपुट के लिए.
Right. That's correct. So, and that is the property. Input impedance or the resistance is infinite, right? So that means it should be something like Ri
Yes.
and R out. So output impedance should be 0.
Zero.
That's why we call this to be with some function. So output impedance is 0. So these are some of the properties. And they should have infinite speed, right? And then the bandwidth should be infinite. इसका मतलब क्या है? They should be able to amplify the signal of all the frequencies, right?
The frequency, yes.
They should be operating the same way in all kind of frequencies. And then there are other things. Common mode rejection ratio, CMRR. That is also infinite, right? इसका मतलब क्या है? That it should be, if something is common, that it will reject that, right? It will not amplify the common signal.
Common signal, yes.
So which is a huge advantage. यानी कि जो noise अगर है, which will be common to both the terminal, right? The signal could be different. So it will not amplify the noise.
Yes.
Wonderful things, right?
Yes.
And then say that slew rate is 0, which is related to the speed, right? Slew rate is infinite. So there should be no lagging time.
Time lagging नहीं होता.
Right.
Output मिल
Or the delay, there should be no kind of slew rate का मतलब है जो भी circuits हैं, how much time they take to respond, right? Right. So these are some of the properties. And now we will discuss some 5 to 6 applications that will help you in your exams. So we will start with the feedback circuit. Feedback क्या होता है?
Output का part input में देना.
Right. So you have operational amplifier. So there are two kinds of feedbacks possible. Positive and negative. This is V out. So I'm taking some part. I'm taking part of this output, not whole. And how will I limit that? Via a resistance, right? Call it R2. And then I have some input. Let me call it V1. So इसको negative feedback बोल रहे हैं, right? Because this is going to the negative terminal. This is 0. So this is an example of feedback circuit. So this part is going. So negative feedback का मतलब क्या है? Negative feedback का मतलब ये है that whatever you are feeding back, so it will try to reduce the output, right?
Reduce, yes.
तो इसका मतलब क्या है? Simply अगर हम बात करें, so if we have this input signal, so let's say if this is expected output, the negative feedback will basically reduce, cut short this output, right? Something like this. This is what you should get. And this is true. Your operational amplifier, they will work, maximum voltage they can draw is the VCC, which is 15 volt. If you're giving any signal which is higher than this, 18 volt or something, let's say if this is at 18 voltage. Remember, ये exam में आ जाता है, right? So this is 18 volt minus 18 volt. Then obviously it cannot go beyond this 15 volt, right? It will be clipped at 15 volt, right? इससे ज़्यादा voltage draw ही नहीं कर सकते. So that is one of the features of negative feedback.
Saturation voltage बोलते हैं.
Yes, yes. So this one is example of an amplifier. इसको हम inverting amplifier भी बोलेंगे. क्यों बोलेंगे? Because V output in this case and V input, so they will be out of phase, so there should be a minus sign. Will come out to be R2 by R1.
R1.
Can you calculate this?
V out.
I can give you a hint that this is the output. This will be at V output, of course, this point. This will be at some voltage. Let me call it VA or VI, intermediate voltage. So this current will be starting from here and the same current will be flowing through this. So यहाँ पे क्या होगा? This V1 minus VI. So V1 minus VI divided by R1.
R1.
That will be your current, right? And same way, this minus this, VI minus V out divided by R2 will be the same current, right? So I can keep both of them equal. And interestingly, VI will be 0. Why?
Virtual ground point.
Virtual ground point. इसका मतलब ये है that V out is basically infinite times V input, right? So this has to be 0. So 0 होने के लिए जितना voltage यहाँ पे है, same voltage should occur here. So this is grounded, so this is also ground. So VI will be 0. This will be 0. You can put both of them equal. You will get this formula. And with this, you can control the gain. So that's the inverting amplifier. Inverting Q because of this minus. So this is an example of inverting
amplifier.
And of course, if you choose R2 equal to R1, then you will get the same output. You can control it.
Unity gain.
Right. This is one example. So
I think it is also called buffer amplifier with unity
buffer
gain.
इसको नहीं बोलते हैं buffer.
अच्छा इसको नहीं बोलते.
Yeah, I'll show you the buffer.
Okay.
So similar to this inverting amplifier, we can have non-inverting amplifier also, right? So non-inverting mein, the only difference will be this voltage will now be fed to this terminal, right? Positive terminal.
Yes.
That's B positive. This is fine. Now this will be grounded. And this is your V1, right? AC signal. So in this case, if you do the same calculation, your V out by V in, now this will be positive because they will be in the same phase. This will come out to be this. So that's the inverting amplifier. Yes, now you were talking about buffer. Buffer is this. Just simply short it.
Okay. अच्छा, inverting configuration.
Yes.
Okay. अच्छा तो मतलब
no, not inverting.
Sorry, non-inverting.
Yeah.
Non-inverting.
Yeah, this is negative feedback and non-inverting. Your input is here, and this you have shorted. So this will become this, right? This is the buffer. So in this case, this will come out to be 1, right? इसको voltage follower भी बोलते हैं. So V out will be V in. In fact, V out will be slightly less than V in, but yeah. So you can, this is you use, as the name also suggests, either voltage follower or buffer. You are basically trying to separate the two stages, right, of your circuit. Then you can use this. So how can we understand it? That the whole of the output is being fed to this input terminal. You can do those calculations. The same, yes. The first one. And you will get V out is equal to V in. The last one, which it was initially made.
वो virtual ground केवल inverting amplifier में possible है या non-inverting में?
You think about it because this is short, right? There is no resistance.
नहीं इसमें नहीं सर, मैं ऐसा पूछ रही हूँ कि अगर
वर्चुअल ग्राउंड दोनों केस में पॉसिबल होगा. तो जो इनपुट वहां पे होगा वो इस वाले पे और या जो इस पे है वो उधर भी अपीयर. तो पहले वहां पे 0 था बिकॉज दिस वाज ग्राउंड. नाउ इट विल बी दैट वोल्टेज, राइट?
क्योंकि सर उसमें इन्वर्टिंग में कैसा होता है कि वी इनपुट भी नेगेटिव टर्मिनल पे अप्लाई करते हैं और फीडबैक रजिस्टर भी इन्वर्टिंग टर्मिनल पे कनेक्ट करते हैं. इन्वर्टिंग में ऐसा होता है, बट नॉन इन्वर्टिंग में ऐसा होता है कि नेगेटिव टर्मिनल पे फीडबैक रजिस्टर अप्लाई करते हैं और जो पॉजिटिव वाला टर्मिनल होता है उसमें वी इनपुट कनेक्ट करते हैं. तो उसमें वर्चुअल ग्राउंड का कनेक्शन फिर कैसे होगा वो थोड़ा समझ नहीं आ रहा मुझे.
This is R2, this is R1, right? Now this point will be same as V input, isn't it?
But it's हाँ ठीक है.
And this is 0, so इसके across voltage क्या होगा? V input minus 0, and the same current will flow through this.
Okay.
Right? इसके along जो current होगा that will be I, and that will come out to be V in divided by R1, and the same current will go here, right? Okay. You can use this calculation. All right. Differential amplifier, which is for what this was initially made for. That now you want to amplify the difference of the two signals. So now you will be applying the input to both the terminals. This is output. And of course, this is for some resistance R1, V1. You're applying the voltage to this. You want to apply the voltage to this also. So this is R1, this is R1, this is R2, the feedback time, negative feedback. And this you will use as a voltage divider. That's a ground R2. V out. So in this case, this is V1, this is V2. So V out will come out to be, the gain will be R2 upon R1. And input will be V1 minus V2 minus V1. Right? This I will not do. This you have to do. क्योंकि ये सबसे ज़्यादा difficult है. And the last two important things are the integrator and differentiator. That's it. So this formula could be very, very helpful. If you remember this formula, you can identify what is R2, R1. You can directly find out the gain. Okay, so differentiator. As the name suggests, कि जो भी input आएगा उसका differentiation output पे appear होगा. इसका derivative. So it uses a capacitor. That's it. So you have an operational amplifier. And then you will get a feedback, of course. And you will call it as some resistance R. And now here you add the capacitor. This is grounded. So remember, this positive feedback, generally, हम philosophy में बात करें, positive feedback is good for psychology and human being. But positive feedback is bad for the transistor, for the operation amplifier. Okay. Negative feedback is useful for. So सारे के सारे circuit तुम देखो, they are made up of using negative feedback, right?
Yes.
V in, this is where we apply. This is some capacitor C, and this is a V out. So this current will start I1.
सर फिर पॉजिटिव फीडबैक किस सर्किट में यूज करते होंगे?
पॉजिटिव फीडबैक,
हाँ, मतलब अभी पॉजिटिव और नेगेटिव बात आई है तो पॉजिटिव कहीं तो यूज करते ही होंगे.
पॉजिटिव फीडबैक हम मतलब जब जॉब करते हैं तब यूज करते हैं ना पॉजिटिव.
नहीं, ओपैम्प में तो नेगेटिव फीडबैक यूज करते हैं.
हाँ, उसमें तो नहीं,
क्योंकि इसमें गेन बढ़ाना है अपने को. लेकिन पॉजिटिव फीडबैक कहाँ यूज करते हैं, कौन से सर्किट में यूज करते हैं?
मैं जानबूझ के नहीं बोल रहा हूँ, बिकॉज़ द मोमेंट आई टेल यू यू विल से कि वो टॉपिक तो रह गया.
ऑसिलेटर. अच्छा, समझ गई मैं.
So I'll send you the notes for oscillator. There we use positive feedback, right?
Okay.
But because those can be designed without using op-amp, they could be designed using various transistors, right? BJT, JFET, MOSFET, CMOS. All right, so this is it. Now again, we know the voltage gain. We output by V input. पहले क्या था? It was R2 by R1, right? Minus R2 by R1.
माइनस में.
लेकिन वहां पे रेजिस्टर लगे हुए थे. यहाँ पे रेजिस्टर की बजाय क्या लगा हुआ है?
कैपेसिटर लगा है और रेजिस्टर.
कैपेसिटर लगा हुआ है. So this you can simply replace R2 by R1 with the impedances, right? Z2 by Z1. What is the impedance in the case of resistance? This is simply R, right? And minus sign, of course. And what is the impedance for this C?
CXC, 1 by
XC,
omega.
right?
Yes.
क्या होता है?
1 by omega C.
I can use the phasor algebra. This will be J omega C.
Okay.
Right?
Right.
So V output is basically minus J omega RC some factor times V input. And this is equivalent to the differentiation. If you have learned the Fourier transform. So this is equivalent to differentiation. And one thing we can see that this is also known as what? Low pass or high pass filter? I don't know.
ये अगर RC है तो लो पास फिल्टर होगा.
So XC is 1 upon क्या होता है ओमेगा, या ओमेगा है ना ओमेगा.
हाँ.
So if you, yes, so
2
XC will be omega C roughly.
Yes.
J omega C, right?
Uh-huh.
So that means that if the frequencies are small, then impedance offered will be very very large. क्योंकि omega denominator में है, right? So if it is a DC, then this will be 0 and you will get infinite impedance.
Yes.
So it will only allow the high frequencies to
High
pass,
frequency.
right?
Yes.
It's a high pass filter also.
RC में.
Isn't it?
Okay.
High pass filter. Let me check. Yeah, high pass filter.
हाँ सर, RC होगा तो हाई पास फिल्टर.
And the integrated is simply just exchange the position of resistance and capacitor. इससे फायदा क्या होगा? The output now will be minus Z1 by Z1 upon Z2. So अब J omega denominator में चला जाएगा, right? It will come out to be minus 1 upon J omega RC, right? Because this is again Z2 by Z1. तो यहाँ पे R हो गया, यहाँ पे C हो गया. So this is Z2 divided by Z1 with a minus sign. So Z2 is nothing but minus 1 upon J omega C, and R is already in the denominator. So now this J omega is in the denominator, which is the inverse of J omega in the numerator. And we know that integration is the inverse operation of the differentiation. So this will give you the integration. That's it.
सर और भी है इसके?
और क्या है?
वही लॉगरिथमिक है, समिंग है, एवरेजिंग है.
या देयर, क्योंकि इलेक्ट्रॉनिक्स तो 100 साल पुराना है ना, तब से लोगों ने क्या क्या डेवलप कर रखा होगा, राइट? देयर आर कंपैरेटर, देन देयर सो मेनी थिंग्स. ऑप-एम्प्स तो लोग आज तक छोड़ ही नहीं रहे, राइट?
अभी भी यूज कर रहे हैं ना सर एक्सपेरिमेंट में, तो इसलिए नहीं छोड़ रहे.
राइट. या ऑप-एम्प्स दे आर नॉट